Hello, everybody. My name is Maximilian Diehl, and I'm a doctoral student at the Chalmers University of Technology in Sweden. And today I would like to present our IROS paper, which is titled Automated Generation of Robotic Planning Domains from Observations. The background of my work is AI planning, which is a popular method to deliberate robots, in particular for longer horizon tasks that requires the execution of a sequence of actions. And the outcome of AI planning is obviously a plan that tells the robot which actions to perform in order to fulfill a goal. Like here in this example, reach, take, put, and then stack. But in order to create this plan, a list of all possible actions, which in this context are also called the planning operators, is required. And these are compiled in a so-called planning domain and usually need to be defined by hand, which is time-consuming or even requires a domain expert. Thus, we implemented a system that automates the operator generation process by considering human demonstrations. Now, one of the advantages of extracting knowledge in terms of planning operators is obviously the modularity. So in this way, we are not limited to merely replicating the demonstrations, but we can possibly apply the extracted knowledge also in new situations. For example, for stacking goals which have not been demonstrated. And the outline of this presentation is as follows. First, we're going to have a closer look into the demonstration phase. Then I'm going to talk about the operator generation process, which is actually the main contribution of this work. Next comes the domain generation and parsing step. And finally, goal definition, plan generation, and execution on a simulated Tiago robotic platform. We start with the demonstration phase. So our action recognition is based on analyzing hand movements in the virtual reality setup. So first, our system automatically segments the whole demonstration into several activities, which are then classified in terms of high-level motions like idle, reach, take, put, and stack. And this classification is based on a decision tree. And the rules of this decision tree, again, are based on parameters that describe the state of the hand. In particular, if there is an object in hand, is the hand moving or not? Is the hand acting on an object? And is the hand open or closed? And since these parameters describe the state of the hand, we also call them hand state variables, as opposed to state variables which describe the state of the environment. For example, is one object on top of another? Now we come to the main contribution, the operator generation. So based on the activity segmentation, we create new operators, and we can give these operators meaningful names corresponding to the activity classification. But we also need to extract the relevant preconditions and effects. And these are made up of all the hand state variables. But additionally, we need to map the hand activities to changes in the environment. For example, in form of environment state changes like on top, which would change when we pick up a cube from the table. And another important part of our system is that it performs abstraction from specific objects and instances to types. So what does that mean? For example, if we observe an activity which is performed with the right hand and it involves the red cube, the operator would abstract that activity to their respective types, like wooden cube and hand. And our system is also continuously adding new operators to the list when new demonstrations come in. So if the operator is completely new in terms of its preconditions and effects, we simply add it to the list of operators. But in case the operator has already been observed before on a previous demonstration, we actually introduced the counter, which keeps track of how often this operator has been observed. And later on, we're going to use this information to prioritize more often observed operators during the plan generation process. So now we're coming to the execution part of our system. So once we're finished with the demonstrations, we can now use these operators for the planning. And in order to be able to access a wide variety of different planning algorithms, we actually wrote a parser that generates a PDDL planning domain from the list of collected operators. And again, I want to stress that this step is completely automated, so we do not need any human effort or time to generate the domains. Also, our operator list is generic, so we could easily add different parsers to other kind of domain descriptions if we would like to adopt a planning algorithm that does not comply with the PDDL format. And then we can use the domain to plan for different stacking goals. And actually we integrated the fast download planning system to generate the plan based on the domain and a user-defined goal or problem. And then this is executed on a simulated Tiago robot. And I want to stress at this point that we assume the lower level commands for each of the high level operators that we extracted to be given. So essentially how to generate execution policies for each operator, for each respective robotic platform you might want to use, that's out of the scope of this paper. And to show the functionality of our system, we have collected in total 12 demonstrations via the virtual reality tool from 3 different participants. So we gave each participant 4 different instructions, namely to stack 1 cube with the left and with the right hand, and then 2 cubes with the left and with the right hand. So 4 demonstrations per participant. And in the middle, you can see several examples of how our system segmented different demonstrations. And one interesting observation was that the segmentation patterns actually were quite different from user to user. For example, due to different demonstration speed, or also small errors as the regrasp, which you can see in the 4th example in the movie at the bottom. So due to these differences, but also due to the fact that we only use the hand state variables, which is only a subset of all the predicates to classify the hand activities, we generally detected several different implementations of one and the same operator type. And again, the operator type is corresponding to the underlying activity classification that this operator is based on. So for example, we observed 4 different configurations of the stacking operator in terms of its preconditions and effects. And here you can see the complete statistics of the operator generation process based on the 12 demonstrations from the 3 different participants. And in total 115 observed activities generated 30 unique operator configurations divided onto the 5 different operator types stack to take. Now, one of the largest sources for possible errors in the operator specification is the segmentation. Since segmentation is not always accurate, and generally we get an accuracy of over 80%, but especially the transition periods are tricky. In other words, it is very difficult to precisely determine the start and end point of an activity. So in cases where an environment change, for example, here the on top predicate change happens exactly during this transition phase, it might be possible it is being ascribed to the wrong activity. And in order to counteract that, we use the operator count as a quality measure, which is being maximized during the plan generation based on the intuition that more often observed operators are also more trustworthy. And for the evaluation, we generated different domains from these demonstrations. So one domain, which we also call the combined demos case, incorporates all 12 demonstrations. So this domain incorporates all the 115 activities that we have retrieved from these 12 demonstrations. But we also generated domains based on all individual demonstrations, which we call the individual demos case. And then we tested the plan generation and execution success based on 4 different stacking goals, which you can see here in this table. And 2 of these goals are actually similar to the instructions we gave to the participants, which is goal 1 and 2. But goal 3 and 4 are new goals, which have been not part of the demonstration. And as you can see, we were able to generate successful plans for all the 4 goals in the case of the domain, which is based on all the demos combined. But even if we just consider 1 demo at a time, we can successfully generate plans for 11 out of 12 of these demos that we have recorded throughout the 4 goals, even goals which have not been demonstrated. So as a next step, we want to expand the applicability of a system to more complex tasks. And one of the biggest bottlenecks of not only our system, but symbolic planning in general is the state variable selection. So for now, we actually work with a minimalistic selection of state variables, comprising the hand gripper related state variables and a few environment state variables like on top of and in touch. But we also want, but if you want to make transition to different scenarios, for example, opening the door, we need new state variables which describe the environment. So of course, we want to minimize the effort of defining grounding, and grounding new state variables. So one option could be learning the state variable representation. Yeah, so to conclude, I have presented our new system that allows us to automatically generate high-level planning operators from human demonstrations, including selection of relevant preconditions and effects, the abstraction from instance to type, and a continuous collection of operators. And we have integrated this operator generation with our activity segmentation and classification process, as well as with a complete plan generation and execution procedure. And that allowed us to successfully plan for different stacking goals, even if they were not part of human demonstrations. All right, so thank you very much for listening to my paper presentation. And now I'm looking forward to a very interesting discussion during the conference.